This is actually my blood. It is fascinating to look at it. While looking at it, I was wondering how it flows and what mathematics describe it. We need this understanding to identify potential problems like clots or blockages that might happen. In this video, we're going to explore 3 algorithms used to simulate different aspects of blood. Each algorithm will answer a specific question. The first question is, what are the mechanical forces in the blood? How fast it flows, for example, so measuring the velocity, what is the pressure in it? To understand this, we start, as in every simulation, by making a set of assumptions. Blood can be approximated as a fluid flowing through a pipe. It enters at the inlet and exits at the outlet. When we look at the cross-section, we observe a velocity gradient. Flow is fastest at the center and slowest near the boundaries. This is a classical fluid dynamics problem described by Bernoulli's equation and continuity equation. Note that the inlet and outlet, since this is a blood vessel, they're not usually described by a single value. It is much more complicated than that. They are often modeled using other models like the Windkessel model. And this what makes it kinda complicated more than just a fluid inside of a pipe. What do we mainly want from this modeling? The wall shear stress. Wall shear stress is the tangential force that flowing blood applies to the inner lining of the artery, especially to the endothelial cells. The endothelial cells are very sensitive to it. They sense the mechanical forces produced by flowing blood, so stable flow generally supports healthy vessel function, while disturbed or low shear regions can activate inflammatory pathways that contribute to vascular disease. The problem is that we can't directly measure wall shear stress through the entire artery inside a living patient. Instead, biomedical engineers reconstruct the patient's artery from medical images and solve the governing fluid equations using computational fluid dynamics, famously known as CFD. Depending on the problem and the software, these equations are commonly solved using numerical techniques such as the finite volume or the finite element method. The simulation computes velocity and pressure throughout the artery. Using this kind of simulation, we can know the wall shear stress and maybe we can assess the potential for a disease. This is not the only question CFD answers about the blood. Maybe we will come to another question in the future. You can follow the channel to know more if you want. Let's move to the next question. Real blood isn't just a fluid with one type of particles. It is a community of different types of individual cells. So to understand that world, engineers need to entirely different way of thinking. So earlier, we know that computational fluid dynamics or CFD tells us how blood moves, but it doesn't tell us how individual cells decide to behave. This is where agent-based modeling comes in. In this approach, each cell is treated as an individual agent that interacts with others according to defined rules. For example, these rules can describe how cells respond to pressure and how they secrete signaling molecules, or maybe how radiation might damage their DNA. And any other rules you want to answer a specific question in a specific scenario. By simulating these interactions over time, we can observe how complex behaviors emerge from simple rules. For example, consider this research. It represents an agent-based model of the vascular wall at the cell tissue scale. The model uses a hexagonal lattice to represent the vessel structure. Rules for which cells behave in this research include processes like mitosis, cell division, apoptosis, which is programmable cell death, cell migration, and the production of chemical signals, and others. Each of these rules define how individual cells behave and interact, ultimately shaping the overall dynamics of the tissue. In the same review article, in this figure, we see a simulation of how a disease in an artery develops over time. It starts with a small number of immune cells in the artery wall, figure A. After 6 months, which is in B, a fatty buildup called plaque grows outward. But the space for blood to flow is still mostly open, with about 40% of the wall affected. By 7 months, in figure B, the plaque keeps growing and begins to narrow the space where blood flows. Now that we have simulated how blood flows and we have simulated how cells interact, there is still one major problem. What works for one patient might not work for another, so why do we still treat patients using averages? What if every patient had a virtual copy of themselves? A digital twin is a dynamic computational model, whether that is like the finite element or the computational fluid dynamics or AI, that continuously learns from real patient data, evolving alongside the individual it represents. For example, in 2020, researchers published the digital twin to enable the vision of precision cardiology. This is a review that talks about the synergies between the mechanistic models, the ones we talked about before, like the computational fluid dynamics or the ABM that involve ruling and understanding, and the statistical models like AI. Maybe we can do a whole video only talking about this subject. Tell me in the comments if you want. So when we put all of this together, you start to see the bigger picture. Computational fluid dynamics helps us understand how blood moves. Agent-based modeling helps us understand how cells behave. And digital twins bring everything together into a personalized, evolving model of a real human being. This is where engineering meets medicine in a very real way. Instead of reacting to disease after it happens, we move toward predicting it, testing treatments before they are applied, and tailoring care to each individual patient. And we're still at the beginning. As imaging improves, as computational power grows, and as data becomes more integrated, these models will only become more accurate and more useful. So the next time you look at something as simple as a drop of blood, remember, behind it is an entire world of physics, biology, and computation working together. And engineers are learning how to simulate all of it. If you found this interesting, consider subscribing because there's a lot more to explore.